Long before astronomers assigned it a formal designation, before its faint trail of reflected sunlight appeared on sky survey images, the object that would one day be called 3I Atlas drifted alone between the stars. It had travelled through interstellar night for uncounted millions of years, its surface frozen into silence by the cold between suns, its structure shaped by forces forgotten by the worlds that once surrounded it. When it finally crossed the invisible boundary of the heliosphere, its arrival was quiet. No flare, no cosmic thunder, only a subtle gleam that betrayed the presence of a wanderer, untouched by any warmth but its own memory. Yet hidden in the light it cast back toward Earth was a secret, a polarization pattern so strange, so disobedient to ordinary physics, that it would come to haunt the minds of those who studied it. Even before anyone understood what it meant, the object's signature had a quality of defiance. Polarization is usually a modest effect, a simple rearrangement of light waves as they bounce off dust, ice, or mineral grains. Most comets, those ancient drifting relics of our own solar system, display predictable polarization curves. The geometry of their dust tails, the harshness of solar radiation, and the grain sizes sculpt the angles with mathematical consistency. But the visitor in question resisted these expectations. The early measurements whispered of angles misaligned with known scattering laws, intensities that rose where they should have fallen, and an eerie smoothness where cometary light is usually wild and chaotic. It behaved not like a piece of familiar celestial debris, but like something shaped by environments alien to the sun, perhaps, alien even to the physics carved into our textbooks. The story of 3I Atlas begins with that tension, the sense that the universe had delivered a messenger too subtle for casual interpretation. It was not the first interstellar object ever detected. Its predecessors, Oumuamua and 2I Borisov, had already prepared astronomers for the possibility that the cosmos occasionally sends fragments of other worlds drifting through our neighbourhood. But 3I Atlas carried a different kind of message. Its strangeness was not in its shape, which was too distant and too dim to resolve. Nor was it in its trajectory, which dutifully traced the hyperbolic arc that defines all visitors not bound to the sun. The anomaly resided in light itself, in how the object coaxed sunlight into a twist, into a dance out of step with familiar celestial choreography. If the early observations felt unsettling, it was because they implied intention where there should be none. Objects do not encode messages. Dust grains do not conspire to confuse. Ice crystals do not deliberately bend photons incorrectly. And yet the polarization curve of 3I Atlas suggested a surface composition or structural complexity profoundly unlike that of our own comets. It glimmered with hints of elongated grains, magnetic alignment, or layered crystals shaped by some foreign astrophysical nursery. Even before the data had been fully analysed, there was a quiet discomfort among astronomers. Here was a traveller bearing the signature of a distant world, a fingerprint from a place humanity would never see. And in that imprint were rules that refused to fit inside the lines drawn by familiar models. As weeks passed, the object continued its silent descent through the solar system, but its faint signal already carried emotional weight. It was not simply another interstellar body. It was a relic of cosmic history, a shard cast adrift from a planetary system that might have flourished or failed long before our own sun shed its first light. In its polarization patterns was the echo of that vanished environment. Each photon reflected off its surface became a tiny witness to the conditions that shaped it, the magnetic storms of a dying star, the shock waves of a supernova, or the delicate chemistry of primordial dust. Light in this case acted not only as illumination, but as confession. It told a story in angles and intensities and curves and subtle shifts, as though the object were trying to reveal the chorus of forces that sculpted it. There is a particular poignancy in studying something that will never return. Interstellar objects pass through once briefly, and then vanish into the dark. There is no second chance to understand them, no possibility of follow-up missions, no orbit to rely on. The scientists who first glimpsed 3I Atlas understood this with quiet urgency. Every observation mattered. Every measurement was a rescue of information that would otherwise be lost forever. And yet even with their precision and effort, the light remained cryptic. It bent in ways that suggested both dust and no dust, both grain alignment and chaotic scattering. It produced a polarization degree that should not have emerged from any combination of compositions known from solar system material. It was as though the object's surface was a mosaic of contradictions, a shell forged by a cosmic environment, where the familiar rules of heating, shaping, and erosion were rearranged into something new. There is another layer to its mystery, one almost philosophical in weight. For most of human history, the universe appeared static, a serene vault of stars whose secrets could be unravelled with patience and logic. But with each new interstellar object discovered, that serenity is replaced by motion, by exchange, by the unsettling realization that worlds do not remain isolated. They fracture, eject, and abandon pieces of themselves to interstellar drift. The odd polarization of 3i Atlas did not merely challenge scientific models, it challenged the emotional assumption that the cosmos is predictable. In its misaligned curves was the reminder that the universe is far older, stranger, and more varied than the conceptual frameworks that human minds attempt to impose upon it. As the object receded into the outer dark, its trail of data remained behind like a lingering question. What had shaped it? What environment had twisted its dust into such unnatural order? What processes had carved such a strange optical signature into its exterior? The opening mystery is not simply that the object came from elsewhere, but that it behaves as though elsewhere means something deeper, more exotic, and more unpredictable than previously imagined. The odd polarization of 3i Atlas was not an anomaly to be filed away. It was an invitation to reconsider how interstellar matter evolves, how planetary systems die, and how light, ordinary, measurable, reliable light can betray the hidden history of places humanity may never explore. Its passage was brief, but the echo of its polarized glow remains, and within that echo lies the beginning of a story, one that continues now, as the search for understanding begins in earnest. When the object that would become known as 3i Atlas first appeared in the stream of a nightly sky survey data, it arrived without ceremony. Automated detection algorithms flagged it as yet another faint mover, a dim point slipping across the starfield with the understated confidence of something not bound to the sun. The discovery belonged to the Atlas survey, the Asteroid Terrestrial Impact Last Alert System, whose wide-field telescopes continuously scanned the heavens in a quiet vigil for potentially hazardous near-Earth objects. Yet hidden within the ordinary cadence of its detections was the seed of a revelation, a trajectory subtly wrong whispering of a birthplace far beyond the outskirts of the solar system. The astronomers who reviewed the coordinates that night were not expecting history. They were simply performing the routine act of cross-checking orbital solutions, confirming that this faint wanderer belonged to the familiar population of long-period comets or minor bodies. But the early fit refused to conform. Instead of the gentle curve produced by bodies gravitationally tied to the sun, the object's motion aligned with the steep, unmistakable slope of a hyperbolic orbit. Its eccentricity exceeded unity, the mathematical boundary that separates returning visitors from those that never come home. The numbers spoke with quiet clarity. This was an interstellar traveller, only the third ever identified. Yet even at this early stage, its light behaved strangely. Atlas's initial photometry suggested brightness variations inconsistent with simple cometary activity. Some observers suspected tumbling, others believed the object might possess a highly irregular surface, but the true anomaly had not yet emerged. Still, those first glimpses were already infused with a certain anticipation, for interstellar objects are not merely scientific footnotes, they are emissaries from distant stellar dramas. They arrive bearing the physics of environments long vanished, and so from the moment its trajectory was confirmed, telescopes across the world shifted toward this dim fragment, eager to extract whatever secrets it was willing to reveal. Follow-up observations came swiftly. The Pan-STAR survey with its panoramic sky coverage provided additional measurements that refined its orbital path. In Chile, the immense eyes of the Very Large Telescope began collecting spectra. In Spain, amateur astronomers pointed their own smaller instruments toward the new arrival, contributing timing data that sharpened brightness curves. This collaborative dance between vast professional observatories and lone observers beneath dark rural skies is a hallmark of modern astronomy, a distributed network of curiosity, each participant capturing another sliver of truth from the same wandering point of light. The scientific community remembered the frenzy surrounding Oumuamua, whose elongated form and anomalous acceleration had thrown models into disarray. They recalled Borisov, whose more traditional cometary activity still bore subtle hints of formation far from our Sun. The discovery of 3i Atlas thus carried with it the tension of a still unfolding pattern, a growing recognition that interstellar debris is not uniform. Each object so far had possessed its own personality, its own defiance of expectations. Against this backdrop, the strange polarization of 3I Atlas would soon carve its own place in the lineage of cosmic anomalies. But in these early days, all that was visible was the anticipation. Observers were eager to determine whether this new wanderer behaved more like Borisov with a familiar coma and tail, or like Oumuamua, whose silence raised questions no one could confidently answer. Polarimetry teams prepared their instruments knowing that light, if analysed through the right prism, could reveal subtle clues. They understood that polarization can betray the shape of grains, the alignment of particles, even the presence of magnetic fields whispering through dust. They knew too that the interstellar medium sculpts its travellers differently than the solar nebula ever could. In Hawaii, where the Atlas system keeps its patient watch, the sky remained clear enough for additional imaging. The faint trail of the object began to lengthen, not from a physical tail, but from the accumulation of successive measurements as it moved. The discovery notes grew more detailed. Interstellar, someone wrote with the tentative punctuation of a scientist, guarding against premature certainty. But the calculations soon removed doubt. The object's speed at infinity exceeded that which even the deepest pull of the sun could explain. This was an outsider, ancient, wandering, and enigmatic. What made this moment remarkable was not merely the identification of a third interstellar object, but the subtle recognition that each detection represents a vast unseen population. For every interstellar body that happens to pass within reach of our telescopes, countless others drift unnoticed through the outer dark. 3I Atlas was thus both a discovery and a reminder. The galaxy is not a quiet sea, but a river of fragments, splinters of worlds long dead, or still forming, each carrying the imprint of places we will never visit. As astronomers coordinated their observations, the first hints of its unusual polarization appeared on instrument logs. The earliest measurements lacked the precision needed to draw conclusions, but they were odd enough to warrant attention. Light from the object was polarized at angles that did not match simple scattering. The degree of polarization showed a slope inconsistent with typical cometary behavior. These discrepancies, though faint, were troubling. Polarization is a sensitive diagnostic. Small deviations can signal profound differences in composition or structure. Soon, observers across continents began to note similar anomalies. Their data points were scattered like stars across a night sky, but a pattern was emerging, a whisper of something foreign. The discovery phase, originally focused on trajectory and brightness, now began to bend toward the mystery latent in the reflected light. It was as though the object had allowed astronomers to approach only so far before revealing a deeper complexity, like a distant melody that becomes stranger as one leans closer. The work of discovery is often romanticized as a moment of revelation, but more often it is the slow accumulation of clues that reshapes expectations. With 3I Atlas, the clues arrived shrouded in ambiguity. The object's faintness made measurement difficult, and small errors could masquerade as exotic effects. Yet the persistence of the anomaly, the refusal of data to align with models, spoke volumes. Scientists felt the first stirrings of unease, not fear, but the intellectual discomfort that accompanies the unraveling of assumptions. Thus, the opening chapter of 3I Atlas's discovery closed with a sense of something unfinished. The identification of the object had been straightforward, but the deeper story, the one encoded in the odd polarization, was only beginning to surface. The telescopes, the observers, the algorithms all had witnessed the arrival of a visitor from another star. What they did not yet realize was that this traveler carried not just the physics of a distant world, but a challenge to the very frameworks used to interpret celestial light. The discovery phase ended with more questions than answers, a fitting prelude to the strangeness yet to unfold. The first clear sign that something was profoundly wrong with 3I Atlas came not from its trajectory or brightness, but from the quiet, mathematically delicate realm of polarization curves. Polarization is an unassuming property, merely the orientation of light waves as they oscillate. Yet it provides a powerful window into the surfaces and dust environments of celestial bodies. When sunlight scatters off grains of dust or crystals of ice, its electric field becomes partially aligned, shifting in measurable ways. Most comets, regardless of their origin within the solar system, follow polarization patterns so predictable that astronomers can often identify grain-size porosity and even age from the curvature of the graph alone. But as the data for 3I Atlas accumulated, the curves refused to cooperate. The first hints emerged from modest polarimeters, small instruments attached to mid-sized telescopes often used for routine comet studies. A few early observations were dismissed as instrumental noise. After all, interstellar objects are faint, stubborn targets. Atmospheric turbulence can nudge polarization measurements into misleading territory. Yet as more teams pointed their polarimeters skyward, the pattern became too persistent to ignore. The degree of polarization was unexpectedly high for an object of its brightness. The phase angle, how the polarization changed as the object reflected sunlight from different aspects of its orbit, showed a slope far steeper than any ordinary comet should display. Instead of aligning with the typical negative polarization branch near small phase angles, 3I Atlas shifted into a regime that suggested either impossibly elongated dust grains or a scattering environment that had somehow learned new physics. This was the moment the anomaly stepped from curiosity into shock. Theoretical models of light scattering are flexible, but only to a point. They can accommodate variations in grain size distribution in the fractal structure of dust aggregates in crystallinity or opacity. Yet none of the established models could produce the specific combination exhibited by the new arrival, a high degree of polarization paired with an unexpectedly smooth, angular dependence, as though the object's surface or coma behaved like a coherent medium rather than a chaotic cloud. Astronomers accustomed to the gentle predictability of cometary polarization found themselves confronting numbers that whispered of contradiction. If the grains were large, the polarization should have decreased. If the grains were tiny, the curve should have shifted differently. If the object lacked a coma and presented only a bare nucleus, the signal should have dropped dramatically. Instead, it hovered in an uncanny zone between categories as though it belonged to none. Some researchers recalled the oddities seen in Oumuamua's reflectivity, though the comparison was imperfect. Oumuamua lacked the pronounced polarization anomalies that now confronted observational teams. Borisov, by contrast, had behaved almost perfectly like a standard comet despite its interstellar birth. 3I Atlas seemed to fall into neither lineage. It was not a tame representative of familiar physics, nor an echo of its predecessors. It carried its own identity shaped by conditions that resisted Earth-based interpretation. As the object brightened slightly during its slow approach, larger observatories entered the fray. The Very Large Telescope in Chile collected high-resolution polarimetric spectra. The Gran Telescopio Canarias joined with its own measurements. Soon the data poured in from multiple hemispheres spread across dozens of nights. The results were consistent, unsettlingly so. Different instruments, different methods, different observers, yet the same anomaly appeared again and again. Systematic error, the refuge of all who hope for simple explanations, grew increasingly untenable. The signatures pointed toward grains that were either unusually elongated or unusually aligned. Elongation alone could not explain the observed behavior. Alignment, however, implied something stranger, still the presence of an external force capable of orienting dust grains in a coherent fashion. Within the solar system, such alignment typically arises only in the presence of magnetic fields strong enough to twist microscopic particles into order. Yet no known solar system comet exhibits significant magnetically aligned dust. Solar radiation pressure outgassing jets and electromagnetic forces act chaotically, not coherently. The neat polarization curve of 3I Atlas suggested a level of order difficult to obtain naturally. A few voices whispered early speculation, perhaps the alignment was fossilized imprinted long before the object entered the solar system preserved across millions of years of interstellar drift. This idea was bold, almost uncomfortably so. It required imagining an environment with magnetic fields powerful enough to sculpt dust grains into uniformity, and stable enough to maintain that alignment over geological timescales. Models of star-forming regions sometimes hint at such fields, but their imprint on larger grains remains uncertain. For many scientists, the shock lay not in the anomaly itself, but in the implications beneath it. If 3I Atlas carried magnetically aligned dust, then it carried a physical memory of its birthplace, an imprint of astrophysical conditions from a distant star system or molecular cloud. Here was a relic of cosmic history encoded not in chemical isotopes or spectral lines, but in the orientation of microscopic grains. To detect such a signature was to glimpse the ghost of an environment long vanished, but the surprise did not end with alignment. The wavelength dependence of polarization, How the effect changed with colour introduced yet another contradiction. In solar system comets, polarization typically increases toward longer wavelengths, tracing the behaviour of irregular grains. But for 3I Atlas, the curve flattened unexpectedly, suggesting a narrower size distribution or a surface dominated by unusually uniform material. This was difficult to reconcile with any known process of grain formation, which tends to produce a messy spectrum of sizes through collisions and fragmentation. Instrument logs began filling with quiet annotations. Unexpected slope non-cometary behaviour requires new model. These notes, while terse, carried the weight of disbelief. When data refuses to bend toward theory, one must either discard the data or expand the theory. And in the case of 3I Atlas, the consistency of independent observations left no room for the former. The scientific community did not leap immediately to dramatic conclusions. Most approached the anomaly with the cautious patience that defines astronomy. Yet the shock was real, not because the object threatened known physics directly, but because it hinted at a complexity beyond current models. It was a reminder that interstellar travellers arrived not as puzzles to be solved quickly, but as invitations to rethink the assumptions underlying entire subfields. The odd polarization curve of 3I Atlas was the quiet but undeniable signal that the universe still harbours phenomena capable of reshaping expectations. What began as a faint point of light had now become a scientific provocation, a contradiction, a hint of foreign processes, a challenge awaiting deeper investigation. The shockwave rippled through teams across continents, urging them to refine instruments, schedule more observations, and prepare for a confrontation with a mystery that refused simplification. The anomaly had spoken. Now the search for understanding would begin in earnest. As the early polarization readings consolidated into a curve that defied the familiar behaviour of solar system comets, astronomers began the deeper work of dissection, peeling back the layers of data in search of any physical process that might restore order to the contradiction. What emerged from this effort was not clarity but a widening fracture in expectation. The light from 3I Atlas seemed determined to resist every attempt at simplification. Each new measurement, each recalibrated instrument, each refined model only sharpened the impression that something profoundly unfamiliar was shaping the reflected sunlight. The first step in the deeper investigation was to ask the most fundamental question: what precisely was scattering the light in a typical comet? Dust streaming from the nucleus forms a tenuous cloud, whose chaotic grains polarize light in predictable ways. The polarization phase curve, how polarization changes with angle, has a characteristic shape, driven by the interplay of dust porosity composition, and the balance between small and large grains. But for 3I Atlas, early models failed to determine whether the dominant scattering medium was a thin coma or the bare surface of the nucleus itself. This uncertainty was itself an anomaly. By examining brightness spectrum and thermal emission, researchers can usually determine whether a comet is actively shedding dust. Yet 3I Atlas seemed to hover between classifications. Its brightness hinted at minimal activity too weak to form a typical coma. Its spectral traces were faint, devoid of the clear gas signatures that accompany outgassing. But its polarization behaved as though dust was present and highly structured. The paradox deepened. How could dust exist without clear activity? How could a weak coma exhibit such strong polarization? How could a bare nucleus produce a curve that required delicate scattering environments, normally found only in diffuse clouds? The Very Large Telescope's deeper measurements attempted to address this ambiguity by probing different wavelengths. If the object carried fine dust, ultraviolet light should scatter strongly. If larger compact grains dominated near-infrared polarization, would reveal their signature. Yet the wavelength dependence refused to align with either model. Instead, the curve flattened where it should rise, steepened where it should level, and at times behaved almost as though the scattering medium were coherent rather than particulate, more like a thin, structured shell than a cloud of individual grains. Further complicating matters were time domain observations. Polarization varied subtly from one night to the next, not in the random manner typical of turbulent cometary jets, but with a faint periodicity. This suggested rotation, yet the periodic signal did not match any of the early rotational solutions derived from brightness variations. It was as if the surface that produced polarization was not the same surface producing the visible light curve. Some speculated that the object's geometry included contrasting regions, patches of unfamiliar material that interacted with sunlight, differently producing polarization spikes when they turned toward Earth. This hint of a variegated surface sent researchers probing the question of composition. Could 3SI Atlas contain exotic ices processed over millions of years by cosmic rays? Could it hide metallic inclusions, crystalline silicates, or fractal aggregates shaped by physico-chemical processes alien to the solar system? Laboratory studies of interstellar dust analogues offered mixed answers. Some grains could produce high polarization under polarized illumination, but not under the diffuse unaligned sunlight of interplanetary space. Other analogues could produce the observed slope, but only with grain sizes too large to remain suspended in a weakly active coma. The object continued to refuse categorization. At this stage, the investigation turned to structure. If the surface of 3I Atlas were covered with elongated, needle-like silicate crystals, possible only in certain high-temperature or strong magnetic field environments, then the polarization might make sense. But high-temperature processing was difficult to reconcile with the object's likely origin in the icy outskirts of a distant stellar system. Conversely, if the grains were porous fractal aggregates, the polarization could be explained, but such aggregates should disintegrate easily under solar radiation. The deeper astronomers looked, the more contradictory the data became. One hypothesis suggested that 3I Atlas might be surrounded by a thin, stable shell of dust, bound by weak electrostatic forces and electrostatic coma. In this scenario, sunlight and charged particles create a layer of dust, lifted only millimeters or centimeters above the surface, suspended by electrostatic repulsion. If the grains in this layer were aligned by the body's rotation, or by residual magnetic fields, the resulting polarization could be exaggerated in precisely the way observed. But this hypothesis required the object to maintain local electric fields strong enough to lift grains without dispersing them, and no known interstellar object had exhibited such behavior before. Another avenue of investigation pointed toward the object's possible birthplace. If 3I Atlas had formed in the magnetized shock front of a dying star, a scenario occasionally proposed for crystalline interstellar dust, its grains might have been imprinted with a magnetic alignment that survived ejection and interstellar drift. In this case, the polarization curve would be not a product of the solar system, but a fossilized memory of its origin environment. Yet models of grain realignment predict rapid loss of orientation once grains are exposed to thermal cycling near a star like the Sun. Why then had 3I Atlas held its signature intact? The investigation grew still more complex as researchers examined the interplay between shape and rotation. If the object had an irregular elongated nucleus, as many suspected from its brightness variations, then its scattering geometry would change dramatically as it tumbled. Yet the polarization remained surprisingly stable across multiple nights, even as brightness fluctuated. This hinted at a decoupling between surface reflectance and dust scattering layers, as though the polarization-generating material existed independently of the rotating nucleus beneath it. Throughout this process, astronomers revisited their raw data, repeatedly searching for instrumental biases, calibration issues, or observational artifacts. None surfaced. The anomaly persisted quiet but insistent. What made the deeper investigation so unsettling was not that 3I Atlas violated established physics. It did not, but that it sat at the intersection of multiple borderline regimes, each pushing known models to their limits. Every plausible explanation required the object to behave in ways unfamiliar to solar system analogues. Grains aligned more coherently than expected, surfaces structured more finely than typical comet nuclei, and scattering environments that resembled neither bare rock nor active coma. By the time the object faded into the background sky, the deeper investigation had reached a sobering conclusion: no single explanation could account for all the data. The odd polarization of 3I Atlas was not merely strange, it was multidimensional, layered, and silently resistant to reduction. It demanded new models, new combinations of environments, new ways of thinking about how interstellar objects preserve the physics of their origins. And in that quiet complexity, it carried the unmistakable sense that its story was only beginning to unravel. The deeper investigation into 3I Atlas had exposed an unsettling truth: its light did not behave according to any familiar scattering regime. But to understand why the polarization was so strange, astronomers turned their attention inward toward the body itself, its surface, its shroud, and the ghostly architecture that governed how it interacted with sunlight. The object, faint though it was, carried enough complexity that every new measurement seemed to reveal another layer folded beneath the last. The first structural clues came from its brightness. Unlike Oumuamua, whose reflectance changed in sharp, abrupt oscillations, 3 Atlas displayed smoother fluctuations coupled at times with sudden but subtle dimming episodes. These fluctuations hinted at surface heterogeneity patches of material, with markedly different albedo possibly alternating between dark carbon-rich crust and brighter crystalline deposits. But the changes were too delicate, too understated to resemble the rough pitted terrains of typical cometary nuclei. Instead, they suggested a surface that had been processed perhaps repeatedly, by forces more uniform than random impacts or chaotic outgassing. This impression deepened when researchers scrutinized the object's photometric colors. Across multiple filter bands, the colors of 3I Atlas leaned toward the bluish-gray of fine crystal ices rather than the reddish tint common to comets coated in organic-rich tholins. This was unexpected. Interstellar travel typically reddens surfaces through cosmic ray irradiation, creating a hardened, chemically altered crust. Yet here was an interstellar object whose tonal signature suggested either recent resurfacing or materials that resisted reddening in ways unfamiliar to solar system chemistry. These findings pushed astronomers to examine the object's reflectance spectra at higher resolution. Although faint and noisy, the spectra carried whispering hints of structure, broad absorption features that suggested crystalline water ice, mixed perhaps with silicate inclusions. But the features lacked the depth expected of a bare nucleus. They were muted as though filtered through a veil. This veil became the next focal point of investigation. If 3I Atlas carried a dust shroud, a faint, nearly invisible halo hugging its surface, then the polarization might be shaped not by the nucleus itself, but by this delicate intermediary. Yet the coma, if present, was astonishingly weak. It did not produce a tail. It did not brighten strongly toward the sun. It did not exhibit the telltale gas emissions that come from sublimation. Instead, it acted like a cloak of dust, held in suspension with improbable stability, dense enough to polarize light, but sparse enough to avoid scattering it into visible diffusion. Researchers began to consider whether the dust grains might be electrically suspended, forming an electrostatic shell just above the surface. In the deep vacuum of interstellar space, grains can accumulate charge through ultraviolet radiation and cosmic ray interactions. If the nucleus had developed regions of differing potential grains, could hover at equilibrium points supported not by gas drag, but by electrostatic repulsion. Such shells have been theorized for airless bodies, including asteroids and the Moon, but never observed with certainty. For 3I Atlas, they offered an enticing possibility, a scattering layer coherent enough to shape polarization, yet subtle enough to escape direct detection. But this solution raised new questions. If the grains were charged, how were they arranged? Why did their alignment persist despite rotational motion? And how could such a delicate structure survive the object's journey around the Sun, where sunlight, solar wind, and thermal stress should have disrupted it? Some models proposed that the dust layer might be rooted in cohesive forces far stronger than those found in solar system analogues. If the grains contained magnetic components, tiny metallic flecks or elongated iron-bearing crystals, then even a weak residual magnetic field could align them into architectures sensitive to incident light. This possibility resonated with earlier hints that the object's birthplace might have been a strongly magnetized environment. A fossil magnetic imprint could explain why the grains maintained a surprising coherence even as the object approached perihelion. The structure of the nucleus itself also demanded attention. Despite its faintness, variations in brightness suggested that the object rotated with a period shorter than early estimates predicted. Subtle changes in amplitude hinted that its shape might be mildly elongated, less extreme than Oumuamua but far from spherical. Elongation affects polarization, particularly when the surface is unevenly covered with scattering material. If one hemisphere harbored a thicker dust layer or brighter crystalline terrain, its rotation could periodically enrich or dilute the polarization curve, producing the faint periodicity detected in early observations. Infrared measurements added yet another layer to the puzzle. The thermal signature of 3I Atlas was lower than predicted for a dormant nucleus of its size. This discrepancy suggested high surface reflectivity, consistent with icy patches or crystalline deposits. But if the object truly had exposed ice, why was sublimation so weak? One possibility was that the ice was unusually refractory, stabilized by exotic chemistry, or locked beneath a shell that allowed light to pass but trapped heat. Another possibility was that the ice was crystalline, not amorphous, a structure that forms only under specific thermal histories, typically associated with environments far more stable than the turbulent outskirts of forming planetary systems. To explore this further, some researchers propose that the surface of 3I Atlas may consist of sintered layers, compacted ice dust mixtures fused into rigid crusts by slow, interstellar heating and cooling cycles. Such layers could resist erosion and preserve the alignment of underlying grains, creating a two-tiered scattering environment, a crystalline surface generating weak reflectance signatures, overlaid by a suspended dust shell that shapes polarization. Yet the most tantalizing discovery came from high-resolution time series data that revealed a subtle polarization anomaly at specific rotational phases. These anomalies appeared not as noise but as coherent dips and rises too regular to ignore. They hinted at the existence of localized regions, perhaps jets fractures or ancient shock-processed patches, where grains were differently structured or aligned. These regions, when rotated into view, altered the entire optical behavior of the object. If real, they represented windows into the object's past, preserved vestiges of the astrophysical episodes that shaped its material long before it wandered into the solar system. Taken together, these clues painted a picture of a surface and shroud, far more complex than those of ordinary comets. 3I Atlas seemed to carry the layered history of a world sculpted by environments. Earthbound observers could barely imagine quiet interstellar heating, magnetic alignment, electrostatic cohesion, crystalline metamorphosis, and ancient shocks. The deeper astronomers probed its surface and dust cloak, the clearer it became that the odd polarization was not a simple anomaly. It was a coded message carved into a world that had drifted between stars. Its surface was a palimpsest, a layered record of cosmic processes that produced a scattering environment unlike anything found near the Sun. Understanding that environment would require not just better models, but a willingness to imagine dust and ice behaving in unfamiliar symphonies. And so the investigation pressed forward, poised on the threshold between known physics and the quiet strangeness of interstellar history. The more astronomers examined 3I Atlas, the more they realized that its surface and dust environment alone could not fully account for the patterns hidden in its reflected light. The next layer of inquiry demanded a shift from the object's physical makeup to the structure of its light itself. This meant turning to the subtle choreography of polarization across time, tracking the minute shifts, the hidden rhythms, the patterns buried in the photons arriving from a world forged under alien skies. Polarization is not static. It breathes, oscillates, and warps according to geometry, rotation, illumination, and the fine-grained structure of whatever medium has scattered the incoming sunlight. For 3I Atlas, astronomers began assembling all available polarimetric data into a temporal map. Each data point was like a note in a faint melody, and as they listened more carefully, a pattern began to form a delicate interplay of angles and intensities that defied the usual randomness of cometary dust. The first hint of structure came from the phase angle dependence. As the object approached the Sun, its scattering geometry changed predictably, allowing researchers to anticipate how polarization should rise or fall. But instead of following the familiar arc, the polarization curve exhibited an unexpected convexity, an extra bulge at intermediate phase angles, as though sunlight were encountering regions of grain alignment, or crystalline surfaces oriented in specific ways. This bulge appeared consistently across observations from multiple telescopes, confirming that it was intrinsic to the object, not an artifact of instrumentation. More surprising still was the slow modulation in polarization degree when data were folded against potential rotational periods. Although the brightness curve remained ambiguous, its fluctuations too subtle to yield a definitive period, the polarization data whispered a different story. Tiny peaks and troughs emerged when the data were aligned with a rotational window near 8 hours. If real, this meant that certain scattering regions rotated periodically into view, even though the brightness changes were too muted to reflect their presence. This mismatch suggested something unusual. The features responsible for polarization were not simple albedo patches. They might be regions where the dust layer thickened or thinned, where crystalline textures shifted orientation, or where the local magnetic properties differed. Some researchers speculated that a rotating magnetic anomaly, a remnant of ancient magnetization, could align grains differently across the surface. As the anomaly rotated, polarization would oscillate without significantly altering brightness. Others pointed toward topographical features, cliffs' ridges or crystalline facets, faintly altering the scattering matrix as they turned beneath the sun. To probe these subtleties, astronomers turned to polarimetric spectroscopy. Instead of measuring polarization across broad photometric bands, they sliced it by wavelength, examining how light of different colors responded to the object's rotation. This approach revealed the most delicate anomaly, yet a slight wavelength-dependent drift, in polarization angles shifting periodically. Such drifts are exceedingly difficult to produce. They require a scattering medium with subtle dispersion effects, grains, whose refractive indices vary sharply with wavelength or layered structures that act like microscopic wave plates. Certain minerals can exhibit this behavior, mica-like silicates, needle-shaped crystalline inclusions, or elongated organic chains forged in exotic environments. Any of these could in theory impart weak chromatic rotation to polarized light. But no comet observed in the solar system had ever shown a signature like this. Here again, 3I Atlas seemed to whisper of a formation environment, steeped in conditions beyond our experience pressures. We never see temperatures rarely sustained, or magnetic fields far stronger than those that cradle our local comets. As attention-sharpened models began focusing on the interplay between grain size distribution and alignment. By simulating elongated grains, tiny rods, flattened plates, or complex fractal clusters, researchers tested whether any combination could reproduce the observed light patterns. Most models failed. The required alignment was too coherent. The grains needed to be too uniform. But a few extreme cases approach plausibility. In these scenarios, grains were shaped by slow, stable processes, perhaps in the quiet outskirts of a cold molecular cloud or the dusty disk of a young star. Over millions of years, these grains could become unusually uniform, their shapes dictated by environmental constraints rarely matched in the solar system. The possibility of a magnetically influenced dust layer resurfaced with force during these modeling efforts. If the grains carried paramagnetic or ferromagnetic components, tiny ion inclusions, metallic alloys, or magnetite chains, they could align with even a weak magnetic field. Interstellar space laced with ghostly magnetic currents might maintain this alignment over vast time spans. When the object entered the solar system, thermal agitation could disrupt some of this coherence, but preserve enough to produce the distinctive polarization peaks. Moreover, the periodicity suggested a subtle rotation-driven modulation, as the nucleus-turned regions with differently oriented alignment would alternately dominate the scattering cross-section. This would naturally produce the faint rhythmic structure embedded in the polarimetric time series. To deepen the investigation, astronomers compared the polarization curve to those of known solar system comets, with unusual behavior, rare objects with jets, fractured crusts, or crystalline ice exposure. Yet no comparison proved adequate. Some comets displayed enhanced polarization near certain angles, but none exhibited the combination of high polarization, smooth spectral dependence, and temporal coherence found in 3I Atlas. The differences were stark enough that some researchers began labeling the object's signature as belonging to a new class, altogether interstellar polarization regime. Beyond alignment, researchers examined the broader patterns, the symmetry of the curve, the unexpected linearity near small phase angles, the sudden but soft inflection near larger angles. Each feature hinted at fine-scale structures in the scattering environment, perhaps layers of dust stacked by electrostatic levitation, or crystalline surfaces arranged in microfacets. The inflection point suggested that the object's scattering behavior transitioned between two regimes, as though the surface contained multiple materials with differing refractive properties. Subtly, the polarization angle itself began shifting as the object receded into deeper solar distances. The drift was small, barely above the threshold of measurement, but its presence signaled a physical change. Perhaps grains were realigning as temperature dropped. Perhaps dust layers were thinning. Perhaps a portion of the electrostatic shell had collapsed. Whatever the cause, the pattern confirmed a dynamic environment, one that responded to solar forcing not by obvious outgassing but by gentle structural rearrangement. Each new pattern embedded in the light's orientation served to deepen the central mystery. The behavior was rich, intricate, multi-layered, more evocative of engineered optical surfaces than the chaotic terrain of natural comets, and yet nothing artificial was needed to explain it. Nature, given enough time, enough pressure, enough magnetic breath, could sculpt such complexity. But the pattern suggested worlds very different from our own birthplaces, whose physical conditions could coax matter into arrangements never seen around the sun. The deeper astronomers stared into the light, the more the patterns resembled a fingerprint, unique, delicate, and carrying the quiet weight of an ancient origin. The odd polarization of 3i Atlas was not simply a scattering anomaly. It was a mosaic of hidden processes, layered stories encoded in photon angles tracing the history of a fragment that had once orbited a distant star. What the patterns revealed was mesmerizing. What they implied was still more so, for as the puzzle sharpened, it set the stage for the next revelation, a deepening of the mystery that would push the limits of current astrophysical understanding and widen the gulf between what was known and what this quiet visitor carried across interstellar darkness. As astronomers continued unraveling the strange layered signals encoded in 3i Atlas's polarized light, a broader picture gradually began to take shape, one not merely of dust and crystalline fragments, but of the object's physical geometry and the silent choreography of its motion through space. For all its faintness, 3i Atlas was not a passive reflector of sunlight. It was a rotating, drifting architecture sculpted by interstellar erosion, reshaped by cosmic rays and subtly animated by the forces it encountered as it passed through the inner solar system. Its geometry, its contours, its spin, its orientation would prove to be just as revealing as its mineral and dust signatures. At first glance, the object appeared unassuming, a point of reflected sunlight barely distinguishable from background stars. But its light curve contained whispers of shape, tiny recurring variations that hinted at an elongated or irregular form. These variations did not produce the dramatic tumbles seen in Oumuamua, nor the rhythmic pulses typical of structured active comets. Instead, they flickered with the subdued elegance of an object whose symmetry had been softened by unimaginable time. Whatever shape 3i Atlas had been born with it had been eroded, rounded, smoothed by aeons, drifting through the interstellar medium, colliding with grains of dust at hypersonic speeds, absorbing cosmic radiation until its outer layers metamorphosed into glassy crusts. But the faint brightness fluctuations were too gentle to reflect a sharply angular nucleus. Something else was at play, a masking layer that softened the light curve while subtly influencing the polarization. If an electrostatic dust shell truly enveloped the surface, it would dampen brightness variations while enhancing the coherent scattering responsible for its unusual polarization. Thus, the light curve became less a direct measurement of shape, and more an expression of how geometry interacted with the dust that clung to it. To unravel those interactions, astronomers turned toward the object's rotational state. Early estimates had suggested an 8-hour period, but continued monitoring exposed inconsistencies. Certain brightness shifts repeated while others appeared to drift. A more complex explanation began to gain ground that 3i Atlas might not be rotating around a single stable axis. Instead, it could be in a state of non-principal axis rotation, tumbling gently through space, its motions constrained but not synchronized. If true, this tumbling would periodically expose different regions of the surface to sunlight, subtly altering the temperature and electric fields that shape the behavior of suspended dust grains. This possibility was strengthened by the polarization data. The small periodic ripples embedded in the polarization curve aligned more closely with a slow precession than with a simple spin. It was as though the object carried an internal asymmetry, perhaps a cluster of denser minerals, or a region of metallic inclusions causing its rotation to wobble. Such a wobble would enhance the complexity of polarization data as differently oriented regions of aligned grains rotated in and out of view. A shape irregular enough to cause such motion must have been sculpted by long cosmic erosion, suggesting that 3i Atlas had endured a deep interstellar journey, its body slowly hollowed, fractured and reconfigured by forces too subtle to observe directly. Its motion through solar space offered further clues. As it approached the sun, slight deviations emerged in its trajectory, tiny shifts consistent with non-gravitational forces. Such forces usually arise from outgassing, yet 3i Atlas exhibited almost no visible activity. But even weak sublimation from isolated crystalline patches could produce minute reactive forces, especially if the surface was riddled with microfractures. Alternatively, if the dust shell interacted with solar radiation pressure, it could create a barely perceptible force nudging the object off its predicted path. These deviations, though faint, signaled a dynamic surface, a world still responding to solar input no longer inert. The geometry of its dust envelope also played a role. Models showed that if dust grains were aligned either magnetically or electrostatically, their scattering would depend strongly on the orientation between the observer, the sun, and the object's rotation axis. In some geometries, this alignment would amplify polarization. In others, it would mute it. By comparing polarization amplitude with predicted rotational phases, researchers were able to sketch a preliminary profile of the object's scattering geometry, a moderately elongated body, perhaps slightly flattened, wrapped in a thin, uneven layer of aligned grains that clustered more densely along one hemisphere. This uneven distribution suggested surface asymmetry regions with different degrees of dust cohesion or magnetic imprint. One hemisphere might contain a magnetic anomaly, tiny but sufficient to orient grains. Another might be smoother, or have lost its original dust layer during a past encounter with cosmic radiation or stellar winds. Such asymmetry would naturally produce the periodic polarization shifts previously observed. Then came the most revealing aspect: the angular dependence of polarization indicated that at certain phases the object scattered light almost as though it were shaped like a gently curved pane, or a series of microfaceted crystalline ridges rather than the chaotic terrain of typical cometary nuclei. This was astonishing. Microfaceting is rare in comets, but can arise from crystalline ices repeatedly heated and cooled over long interstellar trajectories. If 3I Atlas had endured such cycles, its outer layers might have sublimated and recondensed into layered crystalline terraces that influenced scattering geometry far more strongly than a typical dusty crust. In this view, 3I Atlas became not just a rock drifting through the void, but a sculpture carved by time, a body whose geometry held the imprint of millions of years of interstellar exposure. Magnetic alignment, crystalline surfaces, electrostatic layers, all of these interacted with its motion, shaping the way it bent and polarized sunlight. Geometry in this context became a storyteller. It explained why polarization rose sharply at some angles, flattened at others, and oscillated as the object rotated. Even the direction of its incoming trajectory, its inclination relative to the solar system's ecliptic, hinted at deeper origins. Its steep approach suggested it was not merely flung from a nearby stellar neighbour, but potentially ejected from a system whose orbital plane bore little resemblance to ours. Its geometry and motion were thus both historical artefacts shaped by whatever gravitational upheavals expelled it into interstellar flight. By studying the geometry of 3I Atlas, its elongated form, its tumbling motion, its dust envelope's distribution, astronomers were able to extract a portrait of an object sculpted by ancient forces, collisions, magnetic fields, cosmic rays, and the cumulative abrasion of drifting through the galaxy. And as this portrait came into focus, the mystery only sharpened, for geometry alone could not explain everything. Beneath the patterns of rotation, shape, and scattering lay deeper anomalies that would soon push the investigation toward its most troubling question. Why was this interstellar traveller becoming stranger the closer it came to the Sun? A question that would usher in the true escalation of the mystery. As 3I Atlas drew deeper into the Sun's gravitational well, the anomaly that had been quietly growing at the edges of its behaviour began to intensify. It did not erupt in the dramatic fashion of a comet suddenly flaring with outgassing or fragmenting under thermal stress. Instead, the escalation arrived with the same quiet strangeness that had characterized the object from the beginning, a deepening of patterns whispered through, the polarization curve subtle but undeniable, like an unseen force tightening its grip on the visitor's light. The first sign of escalation appeared in the form of a steepening in the polarization degree slope at intermediate phase angles. Instead of flattening as solar system comets invariably do near these angles, 3I Atlas began amplifying its polarization in a smooth, almost mathematical arc. Observers expected the anomaly to level out as the object approached its closest point to the Sun, where thermal agitation should disrupt any fine-grained dust alignment. But the opposite occurred. Polarization rose, refined itself, sharpened, suggesting that the forces shaping it were not weakening under solar heat but responding to it. This was unsettling. Every comet and asteroid studied near perihelion shows some degree of breakdown, dust layers sag, electrostatic cohesion, weakens crystalline surfaces fracture, and scattering environments become chaotic. Yet 3i Atlas behaved as though the Sun were enhancing the alignment of grains, refining the optical coherence of its dust shell, or awakening structures hidden beneath colder layers. Instead of degrading, the polarization curves gained clarity. Astronomers began to notice another troubling trend. The polarization angle itself started to drift with increasing phase angle, more dramatically than before. This meant that the orientation of the scattered light was rotating in a way that ordinary dust physics could not easily explain. Light scattering off randomly oriented grains has predictable angular behavior, but scattering off aligned grains, especially elongated or crystalline ones, can twist polarization angle in ways that indicate external forces at work. This raised the spectre of magnetization again. If 3i Atlas carried a residual magnetic field, or if the grains were sufficiently responsive to magnetic forces, then the increasing solar-wind interaction near perihelion could strengthen grain alignment rather than degrade it. In such a scenario, the object's magnetic memory would awaken under the influence of the Sun's charged particles, causing polarization to intensify. This idea unsettled many researchers, for no comet or minor body in the solar system had ever exhibited such behavior. But the data increasingly leaned toward the interpretation that some interaction between solar wind-embedded magnetic fields and aligned grains was guiding the observed escalation. Simultaneously, the polarization wavelength dependence began to distort. At larger wavelengths, the degree of polarization rose more sharply. At shorter wavelengths, it began to dip. This split suggested that grain populations were separating larger grains responding differently to heating or electrostatic charge than smaller ones. Such segregation could occur if the dust shell were being partially restructured by solar proximity, exposing new layers of material or dislodging grains that had remained frozen in place during the object's long interstellar journey. Another complication emerged: unusual chromatic shifts appeared during specific rotational phases. Polarization signatures that had once displayed relatively consistent periodicity now showed sharp dips and unexpected spikes. These anomalies hinted that structural changes were occurring on the surface, changes rapid enough to manifest within the timescale of a single rotation, yet subtle enough to evade direct photometric detection. Some interpreted this as surface cracking, tiny fractures forming as thermal gradients swept across the nucleus, exposing pockets of crystalline ice or fresh dust. But if that were the case, the expected increase in brightness never materialized. There were no outburst events, no spikes in gas emission, no visible jets erupting from the surface. Whatever was changing was doing so without releasing significant volatiles. This led to the unsettling possibility that subsurface materials were reorganizing, internally melting, refreezing, expanding or contracting in ways that produced no outward plume, but shifted the orientation of grains trapped just beneath the surface crust. Such changes could drastically alter scattering without visibly altering brightness. Meanwhile, the object's motion began to display tiny but measurable non-gravitational anomalies. These were far smaller than the dramatic acceleration exhibited by Oumuamua, yet they were unmistakable. As solar heating increased, its trajectory deviated from purely gravitational predictions in a way that correlated with the polarization escalation. This coupling was profoundly strange. It suggested that the very processes responsible for the polarization anomaly, grain alignment, dust shell restructuring or surface crystallization, were producing subtle reactive forces. No known physical mechanism could easily connect such gentle changes in dust orientation to measurable shifts in orbit. Some proposed that the electrostatic dust shell, if highly coherent, might produce asymmetric radiation pressure. Others posited micro-outgassing too weak for detection but sufficient to nudge the object slightly. Still others suggested that the dust shell could be absorbing solar photons differently across its surface due to the polarization anomaly itself, creating an imbalance in photon pressure. Regardless of mechanism, the message was clear: the object was reacting to the Sun in ways no interstellar visitor had done before. Then came the most troubling escalation. As 3i Atlas exited its perihelion arc and began receding, the polarization behavior did not decompress or return to earlier levels. Instead, it held its elevated signature far longer than models predicted, as though the object retained a structural or electromagnetic enhancement acquired during its solar encounter. Some joked, not seriously, but not casually either, that the Sun had rewritten the object. Others suggested that the dust alignment had reached a stable configuration during perihelion that would now persist for decades. The escalation of the anomaly, far from clarifying the mystery, turned it from a curiosity into a puzzle that destabilized the frameworks used to understand interstellar objects. Not only did 3i Atlas behave strangely, it behaved stranger as it approached the Sun, defying the expectation that increased solar chaos would strip its structure down into familiar forms. It was now impossible to dismiss the anomaly as noise error or poor modelling. The light was doing something real coherent, deliberate in appearance and complex beyond the reach of conventional cometary physics. What had once been a scattering enigma had now become a phenomenon demanding explanation. And as the mystery deepened, astronomers began assembling theories, some grounded in standard astrophysics, others straining at the edges of what the field dared to consider. Each theory reached differently into the physics of alignment, magnetization, crystallization, and cosmic history. But all shared one haunting implication. Somewhere far from our Sun, in a star system we will never see, 3i Atlas was shaped by forces that left fingerprints across its surface, fingerprints that the Sun could not erase, and that the object itself seemed determined to reveal. The escalation of the polarization anomaly had pushed astronomers into a corner, a place where familiar cometary physics could no longer offer refuge. To move forward, they needed to turn toward speculation, toward theory, toward the delicate edge where empirical data meets conceptual possibility. And the first frontier they approached was the realm of exotic dust grains shaped not by the gentle processes that sculpt the solar system's comets, but by the violent magnetic chemically complex environments of distant stars. If 3i Atlas carried a dust signature so foreign that it twisted polarization into unfamiliar forms, then the key to the mystery might lie in the nature of the grains themselves. Exotic dust theories began with an observation the polarization of 3i Atlas rose more steeply than that of any known comet, yet its wavelength dependence was uncommonly smooth. This combination hinted that the grains were not merely small or large, fluffy or compact, but uniform, a rarity in nature. Dust formation is typically messy, producing a spectrum of grain sizes shaped by collisions, sublimation and fracturing. But certain astrophysical environments can impose order upon dust, and some of the earliest theories proposed that 3i Atlas had been forged in one of these. One candidate environment was a dense molecular cloud, the birthplace of stars. In such regions, dust grains can grow slowly and uniformly over millions of years, coated in layers of ice subjected to gentle compaction and exposed to consistent radiation fields. The result can be elongated grains, fractal aggregates with repeating substructures, or needle-like crystals shaped by cold directional gas flow. These grains polarize light efficiently, especially when aligned by magnetic fields. If 3i Atlas inherited such material without significant alteration, its unusual polarization might be a fossil memory of that ancient cloud. But the smoothness of its polarization curve hinted at something even more specialized grains that were not merely elongated but shaped with precise aspect ratios. Laboratory studies of silicate crystals, carbon chains and ice needles showed that certain shapes produce polarization plateaus at specific angles, similar to the gentle inflections observed in the object's curve. Perhaps 3i Atlas carried silicate whiskers, tiny rods of crystalline rock grown in the debris disks of young stars where magnetic fields guide atomic deposition into linear structures. Such whiskers are rare but not impossible. They have been hypothesized as components of interstellar dust for decades. Another possibility was that the dust grains had been processed in the shockwaves of a supernova. When massive stars explode, they forge high-temperature environments where metals condense into grains under turbulent magnetized conditions. Experiments simulating such environments show that the resulting particles can be needle-like or platelet-like, with high refractive indices and strong polarization potential. If 3i Atlas had formed in the chaotic outskirts of a supernova remnant, or if it had passed through one during its interstellar journey, its dust might bear the imprint of extreme conditions never experienced by solar system comets. These exotic grains could explain the steep polarization rise, but they did not fully explain the nearly crystalline precision of the curve's symmetry. For that, scientists turned to theories involving interstellar annealing. Over millions of years, in the cold dark between stars, cosmic rays and UV radiation slowly reorganize the molecular structure of grains. Ice becomes crystalline, amorphous silicates become glass-like, carbon chains polymerize into long-aligned frameworks. Such annealing could in theory produce grains with consistent optical properties so consistent that they scatter light in uncommonly uniform patterns. But if the grains were so uniform, so meticulously sculpted, why had they not been destroyed or randomized by solar heating near perihelion? This question led researchers to consider the possibility that the grains were highly resilient, perhaps held together by strong chemical bonds or embedded within a cohesive matrix on the object's surface. Elongated grains of crystalline carbon or silicate are far more resistant to thermal alteration than the fluffy aggregates of typical comets. If 3I Atlas carried a crust rich in such grains, it could easily withstand the gentle heating it experienced near the Sun, allowing its exotic polarization signature to emerge with even greater clarity. Some researchers proposed a more radical scenario that 3I Atlas might contain a significant fraction of magnetic dust grains, aligned permanently by a strong magnetic field inherited from their formation environment. Such grains would polarize light in ways that mimic coherent optical materials, producing precisely the kind of smooth-enhanced polarization observed. Magnetite grains, metallic nanoparticles, and iron silicate needles could all serve as tiny compass needles frozen into alignment over geological timescales. In interstellar space, where magnetic fields thread through molecular clouds like invisible rivers, such alignment could occur naturally. If 3I Atlas were a fragment of a body formed in such a region, the alignment could persist until disturbed. This idea gained traction when models showed that magnetically aligned grains could reproduce both the polarization steepening and the chromatic rotation of polarization angle seen in 3I Atlas. But the theory required that the object's dust shell remain undisturbed until its encounter with the Sun, an unlikely but not impossible scenario. Electrostatic forces could hold the grains in place, preserving their orientation even through moderate thermal cycling. Another set of theories centered on porous aggregates. Interstellar grains can grow into open fractal structures with enormous surface area and peculiar scattering behavior. These aggregates can polarize light extremely efficiently, producing curves far steeper than those of compact grains. If 3I Atlas carried an outer layer of such aggregates preserved during ejection from its home system, its polarization signature would naturally differ from any solar system comet. But these aggregates should be fragile. Solar radiation should tear them apart. Yet the object's polarization strengthened rather than weakened. This forced theorists to imagine aggregates more resilient than previously known, perhaps reinforced by interstellar ice or bound by magnetic impurities. Theories also explored the possibility of layered grains particles coated in alternating shells of ice silicate and organic material. Such grains can act as micro-resonators for light-producing wavelength-dependent polarization effects. These effects matched in part the chromatic anomalies observed in 3I Atlas near perihelion. Layered grains, however, require specific thermal histories to form histories possibly available only in the outskirts of cooling protoplanetary disks or in the debris environments of ancient star systems where slow heating and cooling cycles occur over millions of years. As exotic dust theories multiplied, a common thread emerged. The dust of 3I Atlas was not the dust of home. It was dust born under conditions alien to our solar system. Dust shaped by astrophysical forces that our comets never experience. Dust that remembered environments we can only model in equations and computer simulations. But dust alone could not solve the mystery. The escalating anomaly suggested deeper layers yet. Dust could shape light, but some of the object's behavior hinted at forces beyond mere scattering. And as scientists pressed deeper into theoretical territory, they began to consider whether magnetic origins, plasma interactions, or relic fields might hold the next piece of the puzzle. Theories were growing bolder. The mystery was growing darker. And the next frontier lay in forces far more invisible and far more powerful than dust. If exotic dust offered a partial explanation for the strange polarization of 3I Atlas, it did not address the deeper question that now pressed on the investigation. What force had shaped that dust so uniformly, aligned it so coherently, and preserved its orientation across a journey spanning millions, perhaps billions of years? The behavior of the object near perihelion, where its polarization intensified under solar influence, instead of collapsing into chaos, pointed towards something more fundamental than grain shape or ice chemistry. It suggested a structural memory, a silent internal discipline within the object's dust environment. Increasingly, attention turned toward magnetic fields and plasma interactions toward the magnetic origins hypothesis. Magnetic alignment of dust is not a new concept. The interstellar medium glows with polarized starlight because grains align with large-scale magnetic fields, producing arcs of coherent polarization across vast regions of space. But such alignment occurs in diffuse clouds, not in compact gravitationally bound bodies like asteroids or comets. Once grains adhere to the surface of a nucleus, their ability to rotate freely vanishes. Alignment should fade. Random impacts, thermal agitation, and electrostatic mixing should erase magnetic order within thousands of years. The interstellar journey of 3I Atlas, bombarded by cosmic rays, jolted by micrometeorite strikes, heated and cooled, by passing starlight should have destroyed even the faintest hint of coherent alignment, and yet the data whispered otherwise. Polarization curves that strengthened near the Sun suggested that the object's grains were not simply aligned, they were responding. As if some dormant order within the object was being awakened by the solar wind like iron filings stirred by a passing magnet. This possibility, unsettling though it was, opened a new line of speculation. Perhaps 3I Atlas was not merely a bearer of aligned dust, but a remnant of an environment where intense magnetic fields sculpted matter at the moment of its birth. The strongest candidate for such an environment was the protoplanetary disk of a young star. These disks are threaded with magnetic fields capable of influencing dust motion, especially at early stages when grains are small and loosely coupled to the gas around them. In certain regions, particularly near the disk's surface or within magnetically active zones, elongated grains can align with the field, locking their orientation while they grow and aggregate. If 3I Atlas originated in such a region, then its dust might retain a fossil magnetic imprint. Another potential birthplace lay even deeper in the astrophysical catalogue, the turbulent outskirts of a stellar magnetosphere. In the early life of highly magnetized stars, violent flares and rotational storms can create regions of intense field strength, sufficient to align dust as it cools and crystallizes. Such environments could forge grains with embedded magnetic directionality, tiny compass needles welded into the structure of the dust itself. Once these grains become part of a larger body, the alignment might persist indefinitely, unless disrupted by strong mechanical forces. For a dormant interstellar traveller drifting through cold space, such disruption might never come. If 3I Atlas carried magnetized grains, its interaction with the solar wind could produce exactly the kind of behavior observed during its passage polarization, that intensified as charged particles streamed around the object, subtly reorienting grains or enhancing coherence within the dust shell. The solar wind could act as a lens, sharpening the magnetic structure rather than destroying it. Some researchers proposed a more provocative scenario that 3I Atlas itself possessed a faint internal magnetic field, not strong by planetary standards but sufficient to influence surface grains. Such a field could originate from ferromagnetic inclusions, iron-nickel clusters or magnetite deposits, frozen into the nucleus during formation. If the body rotated, this internal field could produce a periodic signature in the polarization curve, matching the faint rotational modulation observed in early data. Simulation showed that even a microtesla-level field roughly comparable to the magnetic field of a strong refrigerator magnet could align elongated grains across a thin dust layer. Over time, this layer would develop coherent scattering properties, capable of producing the smooth, steep polarization signature recorded by telescopes. If such a field existed, it would constitute a relic of the object's distant past, a memory of formation in a region where magnetization was not incidental, but essential. Another possibility connected to plasma interactions. In interstellar space, objects accumulate surface charges through cosmic ray bombardment. As the object approached the Sun, solar ultraviolet radiation and the influx of charged particles could have reorganized these charges, producing electric and magnetic fields that shaped the dust shell. This process, known in theoretical models as plasma-driven dust ordering, has been suggested as a mechanism for creating structured dust layers on airless bodies. Although never observed directly, 3I Atlas's behavior offered tantalizing hints that such ordering might be real. The idea gained momentum when researchers noted that some of the object's polarization anomalies coincided with predictions of plasma sheath formation, a phenomenon wherein a thin envelope of ionized dust and electrons forms around an object as it interacts with the charged particle flow. Such a sheath can align dust grains through electrostatic and magnetic interactions, creating a coherent scattering medium. The solar wind could have sculpted the dust envelope around 3I Atlas into precisely the structures observed. Still, the magnetic origins hypothesis was not without problems. If the object carried aligned grains or magnetic inclusions, why did the alignment persist through interstellar travel? Why had the grains not been scrambled by impacts? Why did the polarization signature grow stronger near the Sun instead of collapsing? These questions suggested that magnetization alone could not explain the anomaly. It had to be combined with something else, structure composition, and geometry, working in concert to preserve alignment and enhance it under solar forcing. And yet the hypothesis remained one of the most compelling frameworks available. Magnetism offered a way to connect dust structure to polarization coherence. It explained the interaction with the solar wind. It accounted for periodic variations during rotation. It provided a natural mechanism for the steep polarization curve and its spectral signatures. But it also pointed toward a startling conclusion. If 3I Atlas carried a magnetic imprint from its birthplace, then its polarization was not merely a scattering phenomenon, it was a record. A memory of a distant star's magnetic heartbeat. A relic encoded in microscopic grains preserved through a journey across the galaxy and revealed only when the object drifted through the charged breath of our Sun. Such a realization pushed the mystery into new territory. Dust could twist light. Magnetism could order dust. But beneath these layers, perhaps something deeper still shaped the object's behavior, something tied to the very minerals and structures of its fractured surface forged in a place whose conditions we can scarcely imagine. And so the theories continued to expand, now turning toward the silent architecture of the object's crust, toward fractures, crystals, and the metallic inclusions that could carry the memory of worlds long extinguished. If magnetized grains and plasma interactions offered one path toward explaining the anomalous polarization of 3I Atlas, another clue waited beneath the fragile dust shell hidden in the fractured layered crust of the object itself. For all the elegance of theoretical grain alignment, the surface of an interstellar wanderer is rarely smooth or uniform. It is a mosaic of ancient scars, chemical residues, crystalline accretions and mineral veins that record the deep history of its birthplace. In the case of 3I Atlas, the polarization signal hinted at a scattering environment shaped not merely by dust, but by the complicated interplay of a surface textured by violent astrophysical processes. The first hints of this came from the object's brightness fluctuations, small coherent variations too subtle to reveal shape, yet too structured to be dismissed as noise. These patterns suggested that the surface was divided into regions with different reflectance properties. But unlike the chaotic patchwork of ice dust and stone seen on solar system comets, the variations of 3I Atlas appeared smoother, almost stratified, as though its surface had been shaped by slow, metamorphic processes rather than quick sublimation cycles. This spurred researchers to consider whether the object carried fractured surface layers, ancient crusts broken and refused over millions of years by cosmic heating and cooling. In the deep cold between stars, objects absorb energy from passing star-like cosmic rays and interstellar shocks. Over time, this exposure drives subtle thermal cycles, encouraging the growth of crystalline ices beneath the outermost dust. When portions of this crust warm and cool unevenly, they crack. Over eons, such fractures can propagate through the crust, creating microfacets that act as mirrors, tiny reflective planes capable of scattering light in coherent ways. If these microfacets were uniformly oriented, perhaps guided by the object's rotational history or by the alignment of grains frozen into the crust, then the surface itself could contribute to the object's anomalous polarization. Crystalline ices are known to produce strong polarization under specific geometries. Silicate crystals, especially elongated or plate-like forms, can polarize light with unusual efficiency. If the crust of 3I Atlas contained a network of such crystals aligned or partially ordered within layers, then its scattering behavior could resemble that of an engineered optical surface. This idea gained traction when astronomers compared 3I Atlas's polarization behavior to laboratory measurements of crystalline water ice grown under vacuum conditions. Crystalline ice exhibits birefringence, a property that can split and reorient polarization. When such ice forms in fractured plates, its effect on scattered light becomes even more dramatic. The smoothness of the object's polarization curve, hinted that parts of its surface could consist of such coherent, crystalline layers built slowly over an immense timescale in the stillness between stars. But how would a fragment ejected from a distant planetary system retain such a structure? The answer may lie in the conditions of its formation. Many interstellar objects originate in the outer reaches of protoplanetary disks regions, cold enough for water, methane, ammonia, and carbon monoxide to freeze into layered ices. Over time, these ices can become stratified, hard crystalline layers buried beneath softer amorphous ones, all interlaced with dust grains of varying magnetization and refractive properties. If the body endured tidal forces during ejection, perhaps passing close to a giant planet or being flung outward by a gravitational resonance, its crust could have fractured into layered segments, exposing crystalline interiors that later refroze into stable configurations. Such layered crystalline crusts could naturally produce the unusual polarization seen in 3I Atlas. Light reflecting from crystalline planes would polarize with orientations sensitive to the surface's internal geometry. Even small patches of crystalline exposure could dominate scattering if their orientation favored strong polarization at certain angles. This would explain why the polarization modulation observed in time series data did not always align with brightness changes. The scattering was controlled not by the surface's reflectance, but by the orientation of microscopic facets and aligned grains. There was another, even more provocative possibility: metallic inclusions. Some interstellar bodies may contain grains of iron, nickel, or magnetite residues from the violent astrophysical environments in which planetesimals form. Metallic inclusions can form in protoplanetary disks where temperatures spike, such as near shock fronts, or within turbulent eddies. These inclusions can become embedded in icy crusts, creating mixed-phase surfaces that scatter light in complex ways. Iron-bearing grains in particular can act as polarization amplifiers. When partially aligned, their high refractive indices bending light at angles difficult for silicates or ices to replicate. If 3I Atlas contained metallic fragments within fractures, these inclusions might produce wavelength-dependent polarization peaks, analogous to those observed near perihelion. The subtle chromatic rotation, noted in spectropolarimetric data, would be consistent with light interacting with materials of high optical anisotropy, crystals, metals, or layered mineral structures. Some models proposed that the object's crust consisted of alternating layers of crystalline ice and dust, rich in magnetite or iron sulfides. Such layering would not only influence scattering, but could also preserve remnant magnetism from the object's formation environment. And if the crust fractured under thermal stress during perihelion, even without releasing significant gas, new microfacets could form and expose deeper, more ordered regions, enhancing polarization without increasing brightness. This notion aligned with the observed escalation polarization grew stronger near the Sun, not because the dust shell became more ordered, but because thermal cycling exposed deeper layers of the crust layers that had been shielded from cosmic erosion during the object's interstellar transit. As these fresh surfaces rotated into sunlight, their crystalline or metallic structures could polarize light far more effectively than the outermost weathered crust. Adding to the complexity, fracturing could also rearrange the dust shell. Electrostatic forces may cause dust grains to migrate along fracture lines, or accumulate in crack valleys, forming localized regions of strongly aligned particles. As the object rotated, these regions would contribute to the periodic modulation detected in polarization data, even if they had no measurable impact on brightness. What emerged from these speculations was a picture of 3I Atlas, as a layered, fractured world, a relic whose crust had been stratified over unimaginable timescales. It was not uniform, it was not simple, it was a geological palimpsest recording episodes of freezing cracking, annealing magnetization, and crystallization, woven together by the quiet physics of interstellar drift. Each layer carried a different scattering signature. Each fracture line created a new optical path. Each crystalline facet shaped the angles of reflected sunlight. If this interpretation was correct, then the odd polarization of 3I Atlas was not an anomaly at all. It was the natural consequence of a complex crust, one that had formed in a distant system, cracked under violent forces, reorganized in interstellar space, and revealed its inner architecture when warmed by the sun. Dust alone could not explain the anomaly. Magnetic fields alone could not explain it. Only a fractured, layered surface world born in a place humanity will never witness could account for the complete symphony of its polarized light. and yet even this deep structural explanation was not enough to fully resolve the mystery. Beneath the fractures, beneath the layers, beneath the crystalline grains, another set of theories waited, rooted not in dust or minerals, but in the very foundations of physics. For some anomalies in 3I Atlas's light hinted at interactions that nudged the boundaries between the quantum and the macroscopic, between relativity and thermodynamics. It was time to examine the frontier where the smallest scales whisper into the largest. By the time astronomers had explored the possibilities of exotic grains, magnetic imprints, and fractured crystalline crusts, a subtle unease had taken root in the scientific conversation. For even after layering these explanations together, dust composition, magnetic memory, electrostatic shells, microfaceted ice, it remained clear that 3I Atlas exhibited behaviours no single physical model could reproduce without invoking combinations of processes that rarely cooperate in nature. The anomaly felt multidimensional, a convergence of effects whose coherence implied deeper structure or deeper physics, guiding the way the visitor bent and shaped light. This unease pushed researchers toward a more daring frontier, the domain where quantum scattering, relativistic heating, photon coherence and surface physics interlace. A domain not speculative in the sense of fantasy, but speculative in the sense that the physics is real, established, tested, yet rarely applied at the scale of cometary bodies. 3I Atlas was small, dark and distant, but its unusual polarization had opened a corridor into investigating how quantum-level interactions might influence macroscopic scattering in ways that are only now becoming detectable. The first entry into this frontier was quantum scattering. At nanoscales, the interaction between photons and particles is not governed by classical optics alone. For dust grains smaller than the wavelength of light scattering, becomes a quantum mechanical process that depends on the particle's electronic structure, shape, anisotropy, and internal ordering. In typical comets, grain irregularity washes out these delicate effects. But if the grains of 3I Atlas were unusually uniform, elongated, crystalline, magnetized, then quantum scattering could amplify their polarization signatures far beyond classical predictions. Me-scattering models, usually sufficient for cometary dust, failed dramatically when applied to 3I Atlas. But when researchers introduced discrete dipole approximations models that treat grains as tiny arrays of interacting oscillators, the results began to resemble the object's measured polarization curve. Such models can produce polarization that rises steeply at certain phase angles and flattens at others, especially when grains have elongated shapes or internal alignment. Moreover, quantum-level resonances within the grain, tiny localized oscillations of electrons, can shift polarization angle in ways impossible under classical scattering. These quantum resonances also exhibit chromatic polarization rotation, a phenomenon seen in some laboratory-grown silicates and carbon crystals. When applied to elongated grains aligned within a coherent dust layer, the effect reproduced faint spectral shifts observed in 3I Atlas near perihelion. Light at different wavelengths twisted slightly in polarization angle, as though passing through a microscopic forest of aligned oscillators, each grain acting like a tiny birefringent prism. But quantum scattering alone couldn't explain why the effect intensified near the Sun. That required turning toward another domain, relativistic surface heating. Although the term sounds dramatic, the relativistic aspect is subtle and rooted in how heat flows within surfaces exposed to intense solar radiation. When small bodies absorb sunlight, the temperature gradient across their surfaces can create tiny rapid expansions and contractions, vibrational changes that propagate through crystalline structures. If those structures contain aligned crystals or elongated grains, even slight thermal agitation can alter their scattering properties in ways that cascade through the object's dust shell. For most comets, this phenomenon is drowned out by gas jets and dust bursts. But 3I Atlas exhibited no visible outgassing, suggesting a crust so stable, so tightly sealed that heat distributed smoothly rather than explosively. In such a stable environment, thermal cycling might excite subtle resonances within crystalline layers, vibrations capable of shifting the orientation of grains or altering the refractive index of certain materials. At perihelion, these resonances could amplify polarization by enhancing coherent scattering among grain populations. Relativistic corrections also come into play when considering the high velocities of dust grains expelled or merely displaced by thermal microfractures. Even small surface shedding events can impart velocities sufficient to alter how grains interact with incoming photons. This is not relativity in the dramatic sense of time dilation or mass increase, but relativity in the quiet mathematical sense, how the direction and velocity of moving grains influence polarization through Doppler-altered scattering. Some models suggested that even minimal motion within the dust shell could produce the evolving polarization angle observed near perihelion. Yet the most intriguing part of this frontier lay in the quantum coherent scattering hypothesis. This idea, still in its infancy, proposed that under specific conditions, highly uniform grain shapes magnetic alignment, and crystalline ordering grains within a dust shell could interact with sunlight in ways reminiscent of photonic crystals. Photonic crystals known from laboratory experiments can manipulate light through ordered internal structures, producing polarization patterns that mimic the coherence found in laser cavities or engineered optical materials. If portions of 3I Atlas's dust layer formed a semi-ordered lattice, perhaps through ancient magnetic alignment or through slow annealing in interstellar space, then sunlight could pass through a medium that was neither fully chaotic nor fully ordered but something in between. Such a semi-ordered lattice could produce sharp polarization inflections and smooth coherence curves almost identical to those measured. It would also be sensitive to temperature, explaining why perihelion heating intensified the effect. As parts of the shell warmed, internal alignment might increase strengthening coherence temporarily before cooling disrupted the lattice once more. This would match the behavior observed as the object approached and receded from the Sun. Another speculative frontier involved photon-spin interactions. Circular polarization, where the electric field of light rotates like a corkscrew, has been detected in some astrophysical environments, often linked to magnetic fields or chiral molecules. While 3I Atlas did not show strong circular polarization, faint hints of non-zero values prompted discussion about whether chiral organic molecules or asymmetric crystalline structures might have played a role in shaping its overall polarization behavior. If even a small fraction of its surface or dust contained chiral molecules products of ancient chemistry in a distant star system, then photon-spin coupling could slightly alter polarization, contributing a subtle layer to the observed complexity. Lastly, researchers considered the role of general relativity in surface heat redistribution. While relativistic gravity itself had negligible influence on the object, relativistic corrections to thermal conduction, important in materials with anisotropic crystalline structures, could in principle produce uneven heating that mimicked the periodicity observed in some of the polarization data. Such corrections are still being explored in materials science, not astrophysics, but applying them to 3I Atlas was not unreasonable. If crystalline layers on its surface had internal structures aligned preferentially along certain axes, heat would propagate unevenly, altering scattering properties rhythmically as the body rotated. Together, these frontiers, quantum scattering lattice, coherence, relativistic heating, photon spin coupling, did not offer a single definitive explanation. Instead, they revealed that 3I Atlas might sit at the intersection of multiple subtle physical regimes. A small, cold, ancient object drifting across the galaxy could easily accumulate quantum-aligned grains, fractured crystalline layers, magnetized inclusions, and thermal histories so complex that their combined effects shaped its light in ways never before observed. In this sense, 3I Atlas became not just a comet-like body, but a quantum archive, a repository of physical histories imprinted at different scales. Dust carried the quantum signature of grain formation. Crystalline layers preserved thermodynamic cycles from interstellar drift. Magnetic inclusions encoded the fields of its birth environment. Even heat flow revealed faint whispers of its internal structure. Its polarization anomaly then may not have been anomalous at all. It may have been the natural expression of a world shaped by physics spanning classical mechanics to quantum coherence. With these possibilities in hand, astronomers turned toward the next step, testing, measuring, and probing these theories with all the tools available before the interstellar visitor faded forever into the dark. As the theoretical landscape surrounding 3I Atlas grew increasingly intricate, stretching from exotic grains to magnetic fossils, from crystalline fractures to quantum coherent scattering, the scientific community confronted a sobering truth. Whatever this object was, whatever shaped its polarized light, its passage through the inner solar system was fleeting. The window for observation was closing. Every hour that passed allowed the object to drift farther from the reach of humanity's instruments and every lost hour meant losing a piece of a puzzle that might never present itself again. If any answers were to be salvaged, they would have to come from the full force of modern astronomy's most advanced tools. Thus began a coordinated campaign, a global mobilization of telescopes, polarimeters, spectrographs, and data pipelines, all trained on a dim interstellar visitor whose signal grew weaker by the night. The challenge was not merely scientific, it was logistical. Observatories in both hemispheres synchronized their schedules to create overlapping windows of coverage, stitching together a continuous observational thread as Earth rotated beneath the sky. In this collective effort, 3i Atlas became a transient star around which the world's scientific instruments aligned. The first line of attack came from ground-based optical polarimeters, the instruments most directly capable of probing the object's defining mystery. Facilities in Chile, Spain, Hawaii, and the Canary Islands conducted rapid sequence polarimetry, measuring the degree and angle of polarization across multiple wavelengths while adjusting for atmospheric interference. The goal to capture a detailed time series map of polarization behavior to trace how it evolved as the object rotated and receded. But polarimeters alone were not enough. To understand the object's dust environment, researchers enlisted the power of high-resolution spectroscopy. The European Southern Observatory deployed its flagship instruments, collecting spectra across optical and near-infrared bands to search for subtle absorption features hinting at crystalline ices, metallic inclusions, or organic molecules. Even faint hints of gas emission CO2, CN, or OH could help constrain activity levels and surface composition. Early spectra proved frustratingly flat, but with deeper exposures and longer integration, time's faint undulations began to emerge, suggesting weak but distinct absorption patterns consistent with crystalline water ice. These features, though subtle, helped anchor models of the surface layers. Meanwhile, radio observatories joined the search. The Atacama Large Millimeter Sub-Millimeter Array ALMA, with its unparalleled sensitivity, targeted emission lines that might reveal dust-size distribution or trace amounts of volatile substances. While ALMA detected no strong outgassing signatures, the silence itself served as crucial data. It confirmed that 3i Atlas was astonishingly inactive, even as it passed through regions where normal comets erupt with gas jets. This inactivity reinforced the idea of a sealed fractured crust, a world whose volatile reservoirs resided deep beneath the surface or had been depleted long before the object's ejection into interstellar space. To probe the object's motion with greater precision, astrometric measurements were conducted using both ground-based telescopes and space observatories. The Gaia mission, though not optimized for rapidly moving objects, contributed precise positional data that allowed researchers to track tiny deviations from purely gravitational motion. These deviations, though small, provided fresh clues about non-gravitational forces acting on the object. Whether from faint sublimation, asymmetric radiation pressure on aligned dust grains, or internal structural changes altering reflectance patterns, these anomalies needed careful analysis. Photometric monitoring from wide-field surveys provided another essential dimension. Facilities like Pan-STARRS, ZTF, and Atlas itself contributed continuous brightness measurements, enabling researchers to refine models of rotation, surface heterogeneity, and dust shell behavior. Photometry alone could not solve the polarization puzzle, but when combined with polarimetry and spectroscopy, it became a diagnostic tool for distinguishing between models. Even minor brightness changes could indicate when specific regions of the surface rotated into sunlight correlations that could then be matched to shifts in polarization angle. Space telescopes provided an additional vantage point free from Earth's atmospheric interference. The Hubble Space Telescope captured high-precision imagery at multiple wavelengths, revealing an object whose coma, if present at all, was astonishingly thin, so subtle that even Hubble's sharp vision barely detected it. The James Webb Space Telescope with its infrared instruments probed thermal emission and searched for molecular fingerprints within the surface layers. Although JWST's observations were limited by scheduling constraints and target faintness, its infrared sensitivity offered rare glimpses into the crystalline structure of the surface, hinting at ordered ice lattices seldom preserved in solar system bodies. Complementing these observations were computational tools, supercomputer simulations that tested theoretical models against the incoming data. Researchers simulated dust alignment under various magnetic field strengths, scattering behavior for elongated grains of different compositions and the effect of thermal cycling on fractured crystalline layers. Some simulations produced polarization curves that resembled the observations, others failed spectacularly. But each iteration sharpened the focus of the investigation, narrowing the field of viable explanations. Perhaps the most ambitious scientific tool brought to bear was time-domain synthesis, combining data taken from different instruments at different wavelengths at different angles into a single cohesive model. This required sophisticated statistical frameworks capable of reconciling uncertainties across datasets, an analytical method akin to reconstructing a three-dimensional object from shadows cast under shifting lights. In this sense, 3i Atlas became an exercise not only in astrophysics but in computational inference, where every photon captured by every telescope formed another data point in an evolving portrait. But even as these tools extracted insights from the fading signal, another challenge loomed. The object was becoming too faint for most instruments to track. Each week it grew dimmer. Each month its polarization signal dipped below detection thresholds. The window was closing faster than models predicted, perhaps due to unexpected changes in surface reflectance, perhaps due to simple geometry. Whatever the cause, it demanded urgency. Astronomers began running last light campaigns, observations pushed to the limits of instrumental sensitivity, capturing data even when the object barely rose above background noise. These were heroic efforts, long exposures in fragile weather windows, sophisticated noise reduction algorithms, and careful filtering of cosmic ray strikes on detectors. The resulting data, though noisy, were invaluable. They provided glimpses of how the polarization curve faded, how the dust environment thinned, and how the object's scattering properties changed as it slipped back into darkness. In the end, the scientific tools brought to bear on 3i Atlas formed an orchestra of precision polarimeters, defining structure spectrographs, probing composition radio arrays, searching for gas-space telescopes revealing thermal and crystalline signatures, and simulations binding all these threads into coherent models. This was the fullest, most intensive observational campaign ever launched for an interstellar object. Every technique modern astronomy possessed was applied, sometimes successfully, sometimes not, to extracting meaning from the light of a visitor that offered mysteries instead of clarity. Yet despite the breadth of effort, no single tool provided the decisive answer. Instead, each contributed a fragment, a shard of truth pointing toward a hybrid explanation, one that blended dust physics, magnetic memory, crystalline geology, and quantum-scale interactions. This mosaic of evidence, though rich, still left a shadow at the centre of the mystery. For all the instruments aimed at it, 3 Atlas remained stubbornly enigmatic, and as the object receded beyond observational reach, the time had come to step back, integrate the data, and ask the most difficult question of all. After everything learned, what does the evidence actually suggest? As the last usable photons from 3i Atlas faded into the deepening dark, astronomers found themselves confronting a sobering task, synthesizing everything the global campaign had revealed into a coherent narrative. The object was gone, lost beyond the reach of telescopes, drifting once more through interstellar emptiness, but its light remained encoded in terabytes of data. Now the work was not observational, but interpretive. After months of analysis, cross-correlation, and theoretical contention, a quiet consensus began to form, not a solution, not a complete theory, but a narrowing of possibilities. The odd polarization of 3i Atlas, it seemed, could be understood only through the interplay of multiple physical processes acting together. The first and strongest conclusion was perhaps the least surprising. I Atlas was almost certainly a fragment from the outer reaches of a distant stellar system. Its uniformity, its dust composition, and its crystalline structures all pointed toward an origin in a cold, magnetically influenced protoplanetary disk. Spectropolarimetric hints of crystalline water ice, combined with smooth polarization curves, suggested a world shaped in stable, low-temperature regions, a reservoir of icy planetesimals analogous to our Kuiper belt but sculpted under different stellar conditions. Next came agreement on the dust environment. No model relying on chaotic, randomly oriented grains could reproduce the object's polarization signature. Instead, the data favored elongated or plate-like grains, with a high degree of internal uniformity. The smoothness of the polarization curve implied that grain size dispersion was unusually narrow, a sign of grains that had grown slowly in quiescent environments, rather than through violent collisions. Such grain populations are rare in the solar system, but could be common in the outer disks of certain stars where turbulence is low and growth occurs through gentle accretion. Perhaps the most widely accepted component of the emerging model involved magnetic alignment. While not every researcher endorsed it fully, the weight of evidence leaned toward the idea that 3I Atlas carried a fossil magnetic imprint, either embedded in its dust grains or preserved within the crystalline crust. The polarization intensification near perihelion was difficult to explain without invoking some interaction between aligned grains and the solar wind. Even modest remnant magnetization could orient grains sufficiently to shape the observed scattering patterns. Magnetic inclusions, magnetite, iron sulfides, or metallic fragments offered natural pathways for this alignment. Moreover, the faint rotational modulation in polarization supported the idea of localized magnetic or mineralogical anomalies across the surface. These anomalies would have rotated in and out of sunlight, producing the small periodic oscillations embedded in the time series data. The lack of corresponding brightness changes suggested that the modulating structures were shallow dust layers or crystalline patches rather than large-scale surface variations. Another element that gained traction was the fractured crystalline crust hypothesis. The thermal evolution of the object, particularly near perihelion, could have exposed deeper, more ordered layers of ice or silicate. These layers, protected from cosmic weathering by overlying crusts, may have retained a degree of structural coherence, behaving like microfaceted optical surfaces. Such microfacets could amplify polarization without increasing brightness, explaining why perihelion produced a steepening in polarization curves without corresponding photometric changes. Similarly, the thermal cycling event near perihelion, too subtle to trigger visible outgassing, could have reconfigured the electrostatic dust shell. A small redistribution of grains aligned by residual magnetic fields or surface electrostatics might have strengthened coherence within the shell. This combined effect of thermal fracture magnetic reorientation and dust shell restructuring provided a way to explain the escalation of the anomaly without invoking exotic mechanisms. The most speculative component of the emerging consensus involved the possibility of semi-coherent scattering regimes within the dust shell. While no direct evidence supported full photonic crystal behavior, the chromatic rotation observed in polarization angle hinted at interactions more complex than classical AE scattering. Quantum coherent scattering, though controversial, offered a framework for interpreting how uniform grains could produce spectral features seen in the data. Most researchers viewed this as an upper limit explanation, a boundary marker showing where traditional scattering models began to strain rather than a definitive answer. But it remained on the table. Theories invoking plasma sheath alignment also survived the culling. Simulations showed that solar wind interactions with a magnetized dust shell could enhance alignment at specific angles. This was consistent with the stability of the polarization curve during the object's slow recession from the Sun, where the effect lingered longer than classical models predicted. Plasma interactions alone could not explain the anomaly, but in combination with magnetic memory and crystalline structure, they offered a natural mechanism for sustaining alignment. Step by step, theory by theory, the field converged on a hybrid explanation, a layered interpretation, dust component elongated uniform grains with narrow size distribution, magnetic component fossil magnetic alignment preserved from birth environment, surface component fractured crystalline crust producing coherent microfacets, Dongtai component electrostatic dust shell responding to solar wind and rotation, quantum component subtle scattering effects emerging from ordered grain structures. Individually, none of these could match the data. Together they formed the first plausible physical narrative. Yet even this emerging consensus came with humility. Many aspects of the object's behavior remained unresolved. Why did its polarization intensify so dramatically near perihelion? Why did the dust shell remain coherent through interstellar travel? Why did its crystalline layers survive ejection drift and solar exposure? Why did it rotate with such subtle modulation? And perhaps most enigmatic of all, what processes in its distant birthplace could have forged such a peculiar combination of dust, magnetism and crystal? The data suggested answers, but only in fragments. Theories converged, but only loosely. The picture sharpened, but not enough to render the object fully understood. In the end, 3I Atlas remained what it had been since its discovery, a visitor from a distant star bearing physical memories that refused to be fully deciphered. Science had narrowed the field of possibility, It had glimpsed hints of the object's origin. It had traced the interplay of dust magnetism and light. But the core of the mystery, the precise mechanism behind its odd polarization, remained slightly beyond reach, like a shoreline glimpsed through fog. All that remained now was reflection on what this fleeting world had taught us, and on what its silence would continue to echo long after it vanished into interstellar night. Long after 3i Atlas dwindled into the abyss beyond Jupiter's orbit, long after its last photons were stretched thin by distance and noise, its mystery remained suspended in the shared imagination of the scientific world. It had come and gone without sound, without spectacle, without the bright plume of a comet or the fractured violence of a shattering nucleus. What it left behind was subtler a pattern in polarized light, a quiet defiance of familiar rules, a riddle composed not in gas or dust but in the shifting geometry of sunlight itself. To understand that riddle was to confront not merely an object, but the vastness of the processes that formed it, sculpted it, and cast it into interstellar space. In the days following the final observations, astronomers gathered every shard of insight into a single evolving mosaic. They considered the object's fractured crust, its layered crystalline ice, its embedded metallic inclusions, its elongated grains and magnetized dust, its whispering hints of quantum scattering and electrostatic cohesion. They considered the remarkable stability of its dust shell as though some ancient order held it together through the chaos of its journey. And they considered the sun's strange role in sharpening its polarization signature, rather than smearing it into incoherence, as though warmth and charged particles coaxed the object's structure into greater clarity. As scientists worked through these pieces, a contemplative tone entered the discourse. This was not merely a physical puzzle to be solved, but a reminder of something philosophical. The universe does not form worlds in identical ways. Our solar system's comets, asteroids, and dwarf planets are familiar forms shaped by familiar forces, but 3i Atlas belonged to none of them. It was built in a foreign nursery in conditions earthbound observers had never seen directly, conditions that imprinted themselves not merely on its materials, but on how those materials shaped the light we captured. The most profound realization was that the object's odd polarization was not an error, not a glitch, not an observational flaw. It was authentic, a true signature of physics operating under a different set of constraints and histories. Through that authenticity, it offered a rare perspective. The universe is forming solids, ices, and grains in ways that stretch far beyond our local experience. Moreover, the very difficulty of interpreting the signal revealed something essential about human inquiry. We know enough physics to model light scattering, enough mineralogy to identify crystalline signatures, enough magnetism to suspect ancient alignment. But when these phenomena converge, when quantum-scale interactions meet macroscopic surface structure, when magnetism meets interstellar drift, when fractured ice meets plasma, the resulting behavior escapes tidy categories. 3i Atlas lived in that borderland where known laws combine in ways that appear alien simply because we have never seen them combined before. In this way, the object became both a scientific anomaly and a philosophical mirror. It forced astronomers to confront the limits of their models, the fragility of their expectations, and the expansiveness of the environments that shape cosmological debris. Each grain on its surface was a relic of a world that does not resemble ours, processed by fields and forces whose textures we have only begun to infer. Each crystalline facet was a page from a book written in a language of temperature cycles, magnetic tides, and interstellar solitude. And yet, for all this depth, 3i Atlas remained quiet. It left no plume. It erupted with no jets. It revealed itself through subtleties, through degrees of polarization, through spectral whispers, through microscopic orientations encoded in the angles of reflected light. Unlike Oumuamua's erratic trajectory or Borisov's vigorous outgassing 3i Atlas, behaved as though it wanted to be understood not in motion but in stillness. It asked observers to look more closely, more patiently, more humbly. In the end, the object's lesson was not that interstellar matter is strange, but that strangeness itself is a fundamental property of the cosmos. Our solar system is one data point. The galaxy is composed of trillions. In its brief passage, 3i Atlas reminded humanity that the rules of matter extend beyond the boundaries of familiar worlds, that the universe's creativity far exceeds the constraints of local physics. And so, as the last models converged and the final papers took shape, astronomers found themselves returning not to certainty, but to wonder. What other materials might drift between the stars? What unseen crystalline architectures might lie locked within distant planetesimal belts? What magnetic histories are written inside grains forged beside alien suns? What polarization signatures might future interstellar objects carry? Each revealing a different fragment of the galaxy's hidden diversity. 3i Atlas did not answer these questions, it simply opened them. It made the night feel larger, deeper, more textured. It transformed a faint point of light into a symbol of everything that remains unmeasured and unimagined. And in doing so, it restored something essential to the act of observing the sky. The awareness that every rare visitor carries the potential not merely to refine our models, but to widen the horizon of what we believe possible. As the interstellar fragment disappeared into the cold silence beyond Saturn, it seemed to fold the mystery back into itself, not withholding it, but carrying it onward into a realm where human instruments cannot follow. Yet the imprint of that mystery remained behind, etched into data, into theory, into the quiet humility of those who watched it pass. It had come from a world we will never see, it returned to a darkness we cannot map. But for a moment in the thin region where sunlight caught its surface, 3i Atlas allowed humanity to witness a piece of the galaxy's hidden architecture, an architecture built of dust of ice, of fractures of magnetic memory, of quantum order, of journeys longer than civilization itself. And now, as its story recedes, the narration softens. The universe grows still again. The visitor vanishes. But the questions it opened linger, glowing faintly in the night. Now the tempo slows. The tension that threaded through the investigation begins to loosen like dust settling after a long, delicate drift. The object has passed. The instruments have gone dark. And what remains is not the urgency of discovery, but the soft afterglow of contemplation, the kind that lingers after a rare celestial event fades beyond the reach of sight. Imagine 3i Atlas now drifting through a region of space, where the sun is no longer a warming presence but a faint pale star behind it. The dust shell that once aligned itself in the solar wind now lies quiet, unperturbed. The crystalline layers beneath the crust cool once more into stillness. Whatever reshaping perihelion performed has already been swallowed by the cold. The object glides weightlessly, returning to the anonymity of interstellar space, carrying with it the echoes of forces long extinguished. In this softened perspective, the mystery no longer presses for explanation. It becomes instead an invitation to remember that every grain in the universe carries a past, that every fragment of matter holds a silent biography. The odd polarization of 3i Atlas, once a scientific riddle, now feels like a whisper from a distant history, a reminder that the cosmos is filled with worlds shaped by stories far older than our own. If there is comfort to be found, it lies in this thought. Mysteries like this remind us that the universe is still alive, with surprises still capable of gentle astonishment. We do not need every answer tonight. Some truths can wait. The stars have patience far greater than ours. And so the story fades, a quiet breath, a final glimmer, a traveller returning to the dark. Sweet dreams!